Hi everyone, this is a video on the method of moving points, which is a powerful Olympiad geometry technique to solve hard Olympiad geometry problems. And so the structure of this video will be roughly, I'll start with an moving points example, and I'll introduce all the theory that I'm using along the way. And then after that, I'll cover the basics that you need to know to actually understand how the theory works. But I think that it might make more sense for the viewer to see the example first so that they can see how it'll be applied at the end. And this is just the first video of a series. For example, in this video, I won't cover moving conics and other more advanced moving points theory, but I'll make sure to cover that in future videos. So with that, I'll just first briefly introduce what moving points actually is. And it's basically you animate all the points in the diagram in terms of one variable like time, let's just say, and then you find the degree of the statement being true. What this means is you say this statement is true if and only if this polynomial in time is true. And we'll have various techniques to find the degree of that polynomial, and then we'll find special cases, the degree of the polynomial plus one special cases where the problem will be true. And then by fundamental theorem of algebra, if a polynomial has degree plus one distinct roots, then it's identically zero. So it must be true everywhere. So in general, moving points is just a method of solving the problems by just checking special cases and then proving that those special cases imply that the full problem is true for every configuration. So with that, let's get started with the example. And this is the USA TST 2015 problem 6. Okay, so the problem says that we have a non-equilateral triangle ABC, and then we have the midpoints of the sides like this. And then we also have the Euler line, which so that's the 9-point circle. And we also have the Euler line, which is is the line between the H and O. So it's something like this. And then we have a point S on the Euler line. And then we have MAS and MBS and MCS intersected again, the 9-point circle, again at Y and Z. The reason I'm saying again is that recall the 9-point circle passes through the midpoints of all three sides. And the task of the problem is to show that lines AX, BY, CZ are concurrent. Okay, so this is a very hard problem to solve synthetically, or even to bash it. It's placed as a problem 3/6, but it's actually very quick with moving points. So you probably don't know any of the theory or the ideas for moving points yet. But as I said, I think it's better to start with an example. So first step for moving points is to choose some set of points in objects in the diagram to fix. So those are not going to be moving at all. So in this, usually in a standard ABC triangle problem with 1 point moving that's not ABC, we'll just fix ABC. So we're going to fix points A, B, C, and then with that, M, A, M, B, M, C, the 9-point circle, and the Euler line are all fixed. And now we have to choose an initial moving point, which will start the process to find all the rest of the degrees. So the logical choice here is S, because S is just a random point on the Euler line. And let's just say S moves with degree 1. Because it's on a line, so we can just move it with constant velocity, so linearly. And then there's something called, and then notice that X is just the result of a perspectivity at MA. I'll introduce that later in the video, but this is just the idea of MA sending S to X. Because this is it's X is the second intersection of MAS with a 9-point circle. So then S to X, so S to X is a perspectivity at MA. And there's a theorem about this perspectivities. is that they preserve degree. So we would say that x has degree 1 as well, since s has degree 1. But one caveat is that when we go from a line to a circle in a perspectivity, we double the degree. And when we go to from a circle to a line, we'll half the degree. So x would have degree 2 here. And then similarly, y and z also have degree 2. And now we're going to find the degree of line AX. So there's a theorem I'll prove this theorem later on in this video. There's a theorem that the degree of the line passing through some certain 2 points, it's called like Sachs lemma. The degree of a line passing through 2 points, PQ, is equal to the degree of P plus the degree of Q minus the number of times P and Q coincide. So, number of times they coincide. So, yeah, so then AX, we know that A has degree 0, X has degree 2. So then the degree of AX is just 2 plus 0 minus number of times A and X coincide, which is clearly 0. So the degree of line AX is equal to 2. And similarly, by symmetry, degrees of BY and CZ are equal to 2. So we have 3 lines all moving with degree 2, and we want to prove that they concur. So there's another theorem, which I'll prove later as well, which states that if we want to prove that 3 lines are concurrent, this statement is of degree the sum of the degrees of the 3 lines. So here the degree of this final statement, that AX, BY, and CZ are collinear, is of degree 2 plus 2 plus 2, which is equal to 6. So basically, the final statement is a degree 6 polynomial in time t. So to prove that it's identically equal to 0, we need to check 7 cases. And this sounds like it's really hard, but it's easier than it might look. For example, I won't address the case in this video because they're pretty easy to check. But you can just take, for example, S is equal to any of these 2 intersections, S is equal to G, etc. And you can pretty easily find 7 cases. So, of course, in a real contest, you're going to have to list them out. But for the purposes of this video, we will not do that. Okay, so now that with this example in mind, let's now discuss the theory that we'll need for moving points. So first, everything is happening in the complex projective plane. This is denoted as CP squared. And what's going on here is that points are denoted with homogeneous coordinates x, y, z. And the property of these points is that if you scale it up by constant, like kx, ky, kz, then these 2 correspond to the same point in CP squared, the complex projective plane. So now you might wonder what happens if z is equal to 0. Because usually this will just correspond to this point, z over z, and then this is usually just 1. But if z equals 0, this is an exception. So it turns out that when z equals 0, you get a non-Euclidean point. So what the definition of that is, so let's just say we have the coordinate plane, we have a bunch of points, and then the non-Euclidean point is a point on the line at infinity, which you can just treat as there's a line at infinity that's passing through all the non-Euclidean points. And some important property about points at the line infinity is that every class of parallel lines, if you have a bunch of lines which are parallel, then they all pass through the same point at infinity. So now some nice benefit of this is that no 2 lines are really parallel now because they all intersect, possibly at a point at infinity. Okay, so that's just what we're working with here. And okay, so now that we've defined the complex projective plane, it makes sense to say some properties about it. So let's just say we have 3 complex projective points, x1, y1, z1, x2, y2, z2, and x3, y3, z3. And they're collinear if and only if this determinant is 0. But in moving points, we don't care about the determinant itself. We just care about its degree. Because like as you remembered from the previous problem here, we want, let's just say instead of proving 3 lines are concurrent, it's basically the exact same. But if we had to prove 3 points were collinear, that we could find the degrees of these 3 points. Like let's just say we determined there are 2, 2, and 2. And then we could find the degree of this determinant by expanding it. It turns out the degree of this determinant is the sum of the degrees of these. And so that basically derives this, because for lines it's basically identical to points. Okay. But now we might notice we haven't really actually defined what degree is. So we might have an intuitive understanding of what it means. We'll just give a rigorous definition. So let's just say we have a point parameterized by time t moving in cp squared. So its coordinates are functions are polynomials of t, and it's a polynomials of t like this. And now let's just say we've reduced it to the simplest form. So a of t, b of t, c of t share no common factor. The degree of this moving point is the maximum of the degrees of these polynomials. Maximum of degree of a of t, b of t, and c of t. And yeah, so now for a degree of a line, let's just say we have a line which is parameterized by, lines are parameterized by 2. And here the reason the point is it's parameterized by time t is we're just saying it's a moving point, so it's not fixed. And recall the moving points are all parameterized by time t, and all the points move with respect to that time t. And moving lines, they have 2 parameters because they move with respect to the time parameter t, and another variable which parameterizes the line, the points which move along the line. So it's basically like this. And the degree of the line is basically what you might expect. It's the maximum of the degrees of these polynomials. Degree of b of t of s and degree c of t of s. Okay, so this is the maximum degree of, this is the degree of a moving line, this is the degree of a moving point. And now, we'll state something about projective maps, which is probably the most important thing that you'll do to find degrees in moving points. Okay, so first let's just define what tethered means. It's pretty simple. Let's just say we have a point P, and then we have a line or conic, let's just say omega. Omega usually denotes a circle, but in here we're just saying it's a line or a circle. And P, we say P is tethered to omega if the locus of P is omega. So for example, let's just say we have actually, I'll just go back to the previous example. So here, and also one thing I must say is that omega has to be fixed. You cannot tether a point to some conic that's moving or whatever. Omega has to be fixed. That's the most important thing, because lots of people make mistakes with that. So now we can just see here that when we fixed ABC in the whole triangle and the Euler line, then S is moving, and then S is tethered to the Euler line, because we're moving S linearly along the Euler line with constant velocity. So clearly its locus is the Euler line. So here S is tethered to the Euler line, and the Euler line is fixed. Okay, so now we've defined what tether means, we can define a projective map. So a projective map is basically, it's just a map that preserves the cross ratio. For example, perspectivities preserve the cross ratio. So let's just say we have a point P tethered to line L1 and a point Q tethered to line L2. And of course, L1 and L2 are fixed by definition of tethered. Actually, let's redefine Q as the intersection, and this point is fixed. The center of perspectivity always has to be fixed. So let's say we're intersecting this line with this line here, and to get another point Q. Then the map from P to Q is projective, because perspectivities preserve the cross ratio. This is a common property. So, and also we can take perspectivities from circles to lines and stuff. For example, we can take a perspectivity from this to this, and this would be a projective map. So any such things of this form projective maps, since it all preserves the cross ratio. This point goes to this point, it's a map. and it's also bijective. And clearly, like lots of like simple like affine transformations are, lots of simple ones are also projective. Like for example, reflecting about a line, like reflecting about a point, translating a point by a fixed distance in the plane, or stuff like that. Like that's all projective, because that stuff all preserves lengths, and cross ratios defined in terms of ratios of lengths. And similarly, like taking homotheties and stuff, that's all projective. And the key result for projective maps is that if you have like a projected map from P to Q, and P and Q always have to be both tethered for a projected map to be defined. So P and Q are both tethered. If you have a projected map from P to Q, basically it always preserves the degree, with one caveat, meaning that if P is tethered to a line and Q is tethered to a line, it preserves degree. So the degree of P is equal to the degree of Q. If P is tethered to a circle or conic, and Q is tethered to a circle, it also preserves degree. If P is tethered to a circle, Q is tethered to a line, it halves the degree. And if P is tethered to a line, Q is tethered to a circle, it doubles the degree. So this is known as conic doubling, because like when you project onto a circle, the degrees are doubled. And when you project off a circle to a line, the degrees are halved. But if like the two things that the points are tethered to like have the same type, then the degree stays the same. And so for example, now if we go back to this example, 2015 TSCP6, now we know that S to X is projective map, because we're taking perspectivity at a fixed point, MA, and X is also tethered. Well, X is defined as the intersection, so S to X is projected. Since S moves with degree 1, that means, and we're projecting from a line, the Euler line, onto a circle, the 9-point circle, we know that X has double the degree of S. So X is degree 2. Okay, so now let's prove Zach's lemma, which states that the degree of a line is equal to basically the sum of the degrees of 2 points defining it, minus the number of times that the 2 points are identical. So the proof is just, we use this determinant property. Also, here I meant it's the collinear if the determinant is equal to 0. So we use this determinant property. Okay, so let's say we have 2 points, and we want to find the degree of the line that they determined. So let's consider any point x, y, z on this line. So then the condition that x, y, z lies on the line determined by these 2 points is just that this determinant is equal to 0. And let's expand out this determinant. So it's x times y1 z2 minus y2 z1 plus y times x2 z1 minus x1 z2 plus z times x1 y2 minus y1 x2 is equal to 0. And all we care about is the degree of this statement. Actually, all we care about is like the degree of x, y, and z. Because recall that, all we care about is the degree of x, y, and z. And it's equivalent to like the maximum degree of these. And so we're basically, all we care about is the maximum of the degrees of y1 z2 minus y2 z1 and the identical things. And notice that this degree, the degree of y1 z2 minus y2 z1 is less than or equal to the maximum of the degrees of y1 z2 and y2 z1. And notice that the degree of y1 z2 is equal to the degree of y1 plus degree of z2. And because recall, these are all polynomials of time t, of the time. And the degree of y1, by definition, the degree of this moving point is the maximum of the degrees of these. So this is less than, let's just call this p and this one q. This is less than or equal to the degree of p. This is less than or equal to the degree of q. So this just gives the Zach's lemma, the degree of the line, because it's less than or equal to the degree of p plus degree of q. And now what about the points coinciding? Then the degree drops by 1. Because if the 2 points coincide, then we have a common factor in all of these. So then we can divide that common factor out and the degree drops by 1. Okay, so now if we go back to this original problem, we're slowly uncovering more and more of the properties that we used here. So we've already had that x, y, and z have degree 2 by the conic doubling. And then ax, by, cz all have degree 2 by Zach's lemma, 0 plus 2 minus 0. And then now all that we have left is to find the degree of the statement that these three lines are concurrent. So let's just say that the three lines are polynomials. Let's just prove that. Let's just say the three lines are polynomials, x1, y1, z1, x2, y2, z2, x3, y3, z3. And then it's these three lines are concurrent from the definition. If x1, y1, z1, x2, y2, z2, this determinant evaluates to 0. So we just want to find the degree of this statement. So this is pretty easy, because if we just expand it out, it's x1 times y2, z3 minus z2, y3 plus dot, dot, dot. We have a bunch of similar terms. And notice that each of these terms here is a product of like sum 3 from this. And notice that the degree of x1 is bounded by the degree of p. The degree of this one here is bounded by the degree of q. And the degree of this one here is bounded by the degree of r, because those degrees are the maximum. So then the degree of this whole thing is clearly bounded by the sum. So basically we've proven, and it's basically identical for the proof that the degree of the statement that 3 points are linear is the sum of those degrees. So now we've derived everything that we know now we've seen all the formulas that we need to know to solve this problem. And as you can see, moving points makes this problem very easy, which shows the power of moving points. And this is just barely scratching the surface of moving points. There's a lot more, like moving conics. You can actually define the degree of a circle, and lots of other cool properties. And I hope that you understood this video, and feel free to comment any questions, because moving points is notorious for being confusing to understand and easy to fake solve. Although the chance of fake solving is reduced if you understand all the concepts well. So definitely feel free to comment or ask any questions, because I might not have explained it the best. But okay, thanks for watching this video.